Luis.
Good morning, good afternoon, and good evening, everybody. Thank you for joining and welcome to Ati Motors webinar series. The purpose of the series is to disseminate information and also help grow the logistics automation ecosystem. Please do expect more in this what is now becoming a popular series. I am Guru Prasad and I work as a solutions architect at Ati Motors. Ati has a diverse portfolio of products ranging from tugging to lifting and purpose-built automation equipment to suit multiple use cases. As you see in the slide here, we have a tugging product and then all the way to a pallet lifting product and many variants in between which help in different use cases in logistics. What is central to all of these products and in fact Ati's portfolio is the use of 3D sensors for best-in-class safety, as exhibited by all products in the portfolio. And to tell us more about it, we have Krishna Panyam, the Chief Software Architect at Ati. Krishna has over 3 decades of experience in software and systems engineering and leads the development of our core software platforms, ensuring that every layer, starting from the embedded to the cloud orchestration, is equally robust, scalable, and future-ready. Krishna's multidisciplinary background, commitment to engineering excellence, and a passion for elegant system design plays a very critical role in shaping the intelligence behind our products. Before joining Ati, Krishna worked in the US for several years, including at Cisco in networking and databases before returning to Bangalore. Krishna has a master's degree in computer science from IISc. Before handing over to Krishna, a couple of comments on the format of the webinar itself. What we'll be doing is present a few slides and at logical breaks, take questions from you, answer questions that have come in on the chat window. So please post your queries in the chat window. We will do our very best to answer all of them. So without further delay, over to Krishna.
Thank you, everyone. Welcome to the webinar. Let's get started. So what's a sensor? A sensor is a device that detects and measures some physical property, right? But in the context of AMRs, we are looking at two different kinds of sensors. One is external sensors, which look at the outside environment. So an example of external sensors are cameras, lidars, ultrasonic sensors, etc. And internal sensors are devices that measure specific properties of things within the AMR. So examples are IMU, which measure the rotation of the AMR itself, or wheel encoders, which measure the rotation of the wheels, etc. But today, we will be mainly looking at external sensors, that is LiDARs and cameras. Okay. The field of view is one of the basic properties of any sensor, and it defines or specifies the extent of the environment that the sensor is able to see. And usually it's defined in degrees, 0 to 90 degrees. And often we talk of vertical field of view and horizontal field of view. The picture here on this slide shows a sample color camera sensor, which has a horizontal field of view of 69 degrees and a vertical field of view of 42 degrees. Given that this is how much of the world that the sensor sees, this FOV is one of the primary factors based on which we choose sensors for any given application. Okay. So let's look at some specifications of cameras and LiDAR. FOV is obviously there. Then we are all familiar with camera resolution. Typically, we hear it say 50 megapixels, etc. Then cameras also specify the frame rate, which is the number of images that the camera provides per second. For example, you may say a camera works at 30 FPS or 60 FPS. They usually provide a range of FPS values. Also, cameras are classified as global shutter or rolling shutter, etc. Examples of camera brands are RealSense, OAK-D, Leopard, etc. Okay. Now let's look at some LiDAR specifications. Again, you have the FOV, which the horizontal and vertical FOV. And then you have frame rate, which is similar to what the camera does, except that here it may be that it is one rotation is considered one frame. We will define some of these terms as we go along. Then we are usually interested in the minimum range and the maximum range of a LiDAR. Now, what is minimum range? The minimum range of a LiDAR, or in general any sensor, is the smallest distance at which it can detect an object. And then in the case of LiDAR, it should be able to provide the range of the object, right? And then the maximum range is important because you will want to probably see objects as far away as possible. And the maximum range is usually specified in terms of reflectivity. So for example, a sensor may have a 30-meter maximum range at 10% reflectivity, which means typically black or dark objects which have low reflectivity, you can see them at a distance up to 30 meters. And then it may say it has a range of maximum range of say 50 meters at 90% reflectivity. What that means is, now if you have objects which are highly reflective, then you can see them at distances up to 50 meters. So as you can see, it's quite important to know the minimum and maximum range of a LiDAR. And then we can also talk about vertical resolution and data rate and so on. We'll talk more about these things as we go along. So some LiDAR brands are Velodyne and Ouster, Hesai, SICK, etc. Okay. Now, what is perception? So perception is the term used for processing of the data from various sensors and to make it available for other layers. For example, like we are going to talk about safety and localization, etc., navigation, etc. So the perception is the process of taking all the data from the different sensors and processing it to make it available for the higher layers. Okay. So here is a sample 3D LiDAR scan with a very high resolution. It has 128 beams. Okay. So let's start with the 2D LiDARs. Now, what is a LiDAR? A LiDAR is actually an acronym, and it stands for light detection and ranging. Most LiDARs measure the range by sending a laser beam, emitting a laser beam, and then receiving it and measuring the time interval between these two events. And then that is converted into a range. Right? They're also often called the time of flight sensors because you're measuring the time of flight. 2D LiDARs have usually one laser beam which rotates around the sensor's axis, generating a LiDAR scan. And what is a scan? It's the set of points which you get from one rotation of the LiDAR. Right? So a 2D LiDAR scan is usually in 2 dimensions. And 2D LiDARs are usually installed near the base of a robot, mobile robots typically, so, to see objects in the XY plane close to the ground. For example, there may be, let's say you install it at 100 mm above ground, then it will see objects only in that plane. It cannot detect objects either below or above that. Okay. Now let's see conceptually, let's take an AMR which is using two 2D LiDARs with a 270-degree horizontal field of view. So in this case, it has two such 2D LiDARs, each with 270. So you can see, for example, that there is a red one here, which is covering these 270 degrees, and there is a blue one which is covering these 270 degrees. So in these two quadrants, you can see that they're both able to perceive objects in this section of the 2D plane, and in this segment and in this segment, only one of them is able to perceive. So this is just a schematic showing how you may have two horizontal, two 2D LiDARs with 270-degree field of view to provide a complete 360-degree coverage. Okay, now let's move on to 3D LiDARs. Okay, 3D LiDARs, as the name implies, see the world in all 3 dimensions. There are different kinds of LiDARs. For example, automotive LiDARs are typically solid state with no moving parts, and they have a narrow field of view of, say, horizontal field of view of, say, 100 to 120 degrees, and vertical also maybe 15 to 20 degrees, mainly because they are focused on looking at the road ahead and not so much at, all around. Whereas mechanical spinning LiDARs, which are built for robotic applications, they usually rotate and have a full horizontal field of view of 360 degrees. So here we show one image of a point cloud from one rotation. That is one LiDAR frame or one scan, which has 40,000 points. And as we said, the 3D LiDAR sees the world in 3 dimensions. So the data, the points from the LiDAR would have X, Y, and Z values. Actually, many LiDARs provide the data range data in spherical coordinates, but they can be easily converted into Cartesian coordinates. Okay. Now, the different LiDARs will have different fields of view. So here is an example where a LiDAR has a small, say, minus 7 degrees of field of view below the horizon, and 52 degrees, which is quite large, above the horizon. So this is designed to be installed close to the ground, and then it can see the ground as well as it can see a lot of the environment above ground. So this is an example of a one LiDAR with a field of view which is um, very specific to a particular application. Okay. Now let's look at a very specific concept of repeating versus non-repeating beam patterns. Most of the spinning LiDARs have repeating beam patterns. Right? But it's important to know that what the non-repeating beam pattern means. So when a LiDAR has a non-repeating beam pattern, it means that the vertical angle of the beam keeps changing as the LiDAR rotates. It keeps changing. So that means that if you leave the LiDAR stationary near an object, as the LiDAR rotates, you get more and more coverage of the points of this on the object. So here we have an example of such a LiDAR looking at a pallet. You can see in the picture, this is the pallet mover with the prongs, the tip of the prongs visible here. And this is the pallet. This is one frame from the LiDAR. And if you're stationary and we look at multiple frames, you can see that it is able to get a much more dense point cloud, which gives us a very good estimate of the pallet. And then we can safely and robustly pick up the pallet. So this is a LiDAR which has a non-repeating beam pattern. Whereas if you have LiDARs with repeating beam patterns, however long you are stationary, you will not, the beams always have the same angle. So you will never see a difference. So it will never increase. The point density will not increase. Yeah. Now we come to the concept of sensor fusion and calibration. Now, what is sensor fusion? Right? Let's say you have two LiDARs. You have a LiDAR in front and you have a LiDAR at the back. Now, to be able to combine them into a single point cloud, what you need to do is to rotate the point cloud from the LiDAR at the back by 180 degrees, and then maybe translate both of them to a single frame of reference, and then you can combine them. Right? So this is the kind of transformation that you need to convert the point clouds from each sensor into a single frame of reference. And often the sensors may need some corrections or some filters that may need to be applied. For example, cameras see a lot of reflections, and often some LiDARs also see reflections. So we may need to correct them, or we may need to handle them in some way. So such filters may need to be applied. And then some sensor calibration. Let's talk about sensor calibration. So sensor calibration consists of extrinsic and intrinsic calibration. So in extrinsic calibration means something referring to the position of the sensor relative to the AMR or position with respect to other sensors, right? So this is the physical distance and the orientation of the sensors with respect to each other and with respect to the AMR itself. And the intrinsics are something to do with the sensor's own internal calibration. So different sensors may provide means to calibrate in their internal intrinsics. Okay, so here we have an example of why or what a good calibration will do. So we have again a pallet mover trying to pick up a pallet with a load on top. And you can see on the left-hand side, we have an image where the data from the camera and the data from the LiDAR do not coincide very well because of some poor calibration. And the image on the right-hand side shows that once you apply, once you get a good calibration and apply that, before you do a sensor fusion, then you get much better overlap of the two sets of data, and then that results in a robust sensor fusion and further processing. Okay, so often people ask, aren't cameras 3D and aren't they enough? Right? Do we really need 3D LiDAR? So cameras have a lot of good things happening. Cameras see the world in 3 dimensions, and also cameras have a lot of data, dense data with semantic information. For example, cameras can see color and cameras can see texture. All of these are very useful for object recognition. For example, I'm sure all of you have come across various machine learning tools and AI tools which do wonderful things by looking at camera images and detecting obstacles and doing a lot more. For example, YOLO is one such thing. And then you also have depth data. So if you look at these two images, this is the color image and this is the depth image. And it shows each point here has a value, and we have color coded it based on that. So the red points have a depth which is far away, and the blue is closest, and the in between values are the other colors are in between. So so then this depth data allows us to actually exactly say how far each point of this chair and the pallet, etc., or how far away they are. So in a sense, this can be converted, the camera image can be converted along with the depth information into a point cloud. Right? So in that sense, they do get close to the LiDAR. But let's see what are the limitations of the camera. Right? If you remember from the first slide, the camera, I mean, that camera had a horizontal field of view of 69. You do get cameras with a larger FOV, but most of them typically do have a narrow FOV, which means that, for example, if you take that camera with 69 degrees, now when you're doing a very sharp turn, a large portion of your path ahead, immediate path in front of you, ahead of you, may be not visible in the camera, maybe outside the camera's field of view, right? Which means that now if you have an obstacle, the camera is unable to see that. Which again, what follows then is that you may need multiple cameras to cover the area of interest. Okay, that is one problem. And when you have multiple cameras, then again, you need calibration and sensor fusion, etc., which all adds to the computation and the cost. And then lighting is a major limitation. Like you can see in the third image here, this is a common occurrence in many industrial settings where suddenly there is a bright light that that obscures everything, and you really cannot make much sense out of this image. So it's not very reliable when you have such an environment, and the camera becomes not very reliable in such settings. And cameras have other known problems. For example, reflections, as I mentioned, or when you see repeating patterns like a rolling shutter, etc., the camera often gets confused and the depth values may be unreliable. So given all of this, I would say that the camera is a great tool to augment, great sensor to augment the 3D LiDAR, but it's not really, you can't really build this robust solution using just cameras. Okay. So for example, let's say, let's just think and say, let's say somebody says, well, if I have 6 cameras, I can see all 360 degrees, and why can't I build a solution with that? So if you really think of that, as I already said, you would need calibration, you would need sensor fusion, and even then, the 6 images, the point clouds may be combined, but the 6 images cannot be combined into one. So how do you handle that, and so on? So So again, cameras are a very nice thing to augment a 3D LiDAR, but it cannot replace a 3D LiDAR. Finally, we'll come to placement of 3D LiDARs. So where can you place? We saw that the 2D LiDARs are typically placed close to the ground. So for example, if this is an AMR and we have to place a 2D LiDAR, we would place it somewhere here, which would give a complete visibility of the plane, at least in the front of this AMR. Right? But let's say we have a spinning LiDAR which has a 360-degree horizontal field of view and a large vertical field of view. Like we can take this example. This one has a 42-degree vertical field of view and a full 360 horizontal view. And we would like to install it usually on the top of the robot to get a clear visibility of the surroundings, which has lots of advantages, as we will see in the following slides. But the one unfortunate side effect of that is that depending on the height of the LiDAR, you will get a blind spot. As you can see, this dark area is the blind spot. This whole cone from here to, say, in this case, about 2 meters from the base of the sensor, you would have a blind spot. And we will see how to handle that. Okay, but in general, the number of 3D lidars and where you place them, etc., depends purely on the application. This particular Sherpa XT is meant for tugging, and it does not need to go in reverse. So we are able to move the camera position slightly forward of center so that we get good visibility in the center, in the front. Okay. So, but then there are other applications. For example, you may need to carry a load on top, like in a lifter, in which case, obviously, you cannot place the LiDAR on the top of the AMR. And then if you need to move in reverse or if you need to do a full 180-degree turn, etc., you may need other additional sensors. Okay. Okay. So that concludes the first section. Guru, we have any questions?
Yeah, there are a few questions. I'm going to read them to you. One of the first questions that I see is we talked about reflectivity of the surface that receives the LiDAR beam. Given that reflectivity is an important aspect, the question was really, can LiDARs detect objects in the dark? I guess the reflectivity that you mentioned is perhaps slightly different from the reflectivity in the question, but I'll leave it to you to answer the question.
Yeah, so LiDARs don't need external light. So the LiDAR itself is emitting a laser beam. So it does not depend on external light. We are talking of the reflectivity of the object that is being perceived. That means that, let's say, a person who is walking in front, or a tire. For example, a tire is fairly dark and not very reflective, whereas a shiny metal surface of the car would be highly reflective. So that's what we are talking about. And the LiDAR does not depend on the ambient light, unlike the camera.
And there's another question on, can you give us some sense of the data rate? Let's assume it's a 32 beam LiDAR and spinning at 10 FPS. Can you talk a little bit about how much data I should be ready to process per second?
Okay. So when you say 32 beam, that's usually what you call the along with the vertical field of view. We talk of that as vertical resolution. And the horizontal resolution, typically most of the lidars, spinning lidars, let you choose different horizontal resolutions. So let's take an example of, say, 1024. That means that for each sweep or each frame, each of the 32 beams gives you 1024 points. Each of the 360 degrees is the 360 degrees of one sweep is divided into 1024. So we are going to get in one LiDAR frame, we are going to get 32 times 1024 or 32,768 points. That would be one frame.
There's a small
and
question
then if you
on
have 10F, sorry.
Yeah, of course,
yeah,
300,000. One more question. You did mention about non-repeating beam patterns.
Yeah.
Now, when you say non-repeating, is the play achieved by varying the vertical angles or the horizontal angles or both?
Um, well, I've not really done much research into how it's done, but I believe that it's the vertical angles, vertical beam angle is what is varied by using mirrors, not the horizontal angles. The lidar still goes around the vertical axis, but the vertical angle of the beam is varied using some arrangement of mirrors, is what I understand.
Okay. Yeah. The last question on that is typically what is the accuracy that we see in radars?
Okay.
Is
That
there
again
any standard
varies.
deviation or variance that you can,
Uh,
without naming any product, is it possible to
Yeah,
comment?
I would say it's, I mean, it varies and it may vary from, say, 1 centimeter to 5 centimeters is typical of, in terms of the accuracy. But then there are newer ones which are, much more precise and probably cost a lot more as well. But yes, it's possible to get very high precision and accuracy with 3D lidars.
That's good to know. That's all questions we have on the first section. Perhaps you can
Okay.
continue on to the next.
Yeah, let's move on to the safety. Okay, so there's a lot of stuff on this slide, so let me try and explain what's happening here. So these two images represent one a LiDAR point cloud, one LiDAR frame. This is the three-dimensional point cloud, and this is the two-dimensional point cloud. And this is the camera image, and this is the corresponding depth image. And when we combine the point cloud from the LiDAR and from the camera, and then we merge that with the predicted path of the AMR. As you can see here, this is what we get is something called the drivable space. So in this, we show the robot's position in magenta. Most of the images going forward will have this. They will show the position of the robot in this color. And the gray dotted line is the predicted path of the AMR, and the light blue is the swept path, that is with some safety, etc. How much space does the robot need to move forward? And then we see that there is some object that was seen, and that is on this predicted path. And now that is considered an obstacle. Now we have other points here, which all the red ones are things that are seen, like for example, the small red thing inside the dark circle is this another AMR. And so since that is on the path and we are likely to collide with it, it's considered an obstacle. And based on that, and based on the distance, the robot will take appropriate action, which may be to stop the vehicle or to slow down and maybe play some warnings message or sound, change the indicator lights, etc. Right? So that is typically what happens in terms of combining the data from the different sensors and combining the path information, and then to say whether we are likely to have a collision or not. So this is for, let's say, this is the static obstacle detection. When object tracking is enabled, then we would also track, let's say, for example, this object, whether if it's moving, then we would track its velocity, and then we would try to predict its position in future and see if it is likely to collide, and even that would be treated as an obstacle. So this is the overview of the safety mechanism. Obviously, I'm simplifying everything to make things clear. There will be a lot of other things that are not discussed here, but this should give you a good idea of how the sensors, how the data from the sensors is used to make for safety. Okay, so now let's look at a 2D lidar. How we get safety with a 2D lidar. So as we already said, the 2D LiDAR senses the environment in a single plane, which is close to the ground. So on the right, you see two sample images, one from a 2D LiDAR and one from a 3D LiDAR. As you can see, the 2D LiDAR provides very sparse data, and it is able to see data in only a single plane. So it is not going to see any objects above or below that. And this rectangle is the AMR's position. So the good thing about the 2D LiDAR is that given it's restricted to single plane, it is very good at detecting small obstacles at that height, right? At that single height, it is very good at that. But on the other hand, it has a lot of limitations because it cannot really see much beyond that single plane. It may not be able to detect or distinguish between a ramp. A ramp is just a slope between two floors, two horizontal surfaces. It may not be able to distinguish between a ramp and a real obstacle. So which means that now you are restricted to operating your AMR on a smooth surface or smooth floor only. You cannot operate it on a ramp because it would see the ramp as an obstacle by itself. Okay. And there are many other objects which are fairly common in industrial settings. For example, overhanging obstacles like vertical sliding doors, which are often placed between two sections of a plant to keep things clean, or a swinging barrier, or a industrial PVC strip curtain, etc. So many of these things, if they're off the floor, then the 2D LiDAR may not be able to perceive it. And another limitation is that the amount of data that you get from a 2D LiDAR is very limited, very sparse, which makes it difficult to do object tracking. Right? Now let's see how 3D LiDARs do. Okay, so here is an example of a 3D LiDAR. So on the right-hand side in the camera image, you can see a large traffic barrier, which is actually protecting access to an open lift, which goes up and down. So you can see that this is the barrier, and there is the floor ends here. And when the lift comes up, then the barrier goes up along with that, and you are able to move. So you can see clearly in this 3D LiDAR scan that this is the AMR and we are looking over its shoulder. And you can see that it clearly sees both the bottom and the top of this barrier, along with many other things. And then these gray points, the gray circles are the ground points, and the AMR can perceive that even without the barrier. From the lack of ground points at this point, it should be able to perceive that there is no floor there, and it's not safe to move in that area. So this is an example of where a 3D LiDAR sees a much rich set of data from the environment. Okay. Now here's another example where the camera image shows the AMR in front of a ramp, and the picture above shows the top view of a 3D LiDAR scan. And all these gray, this is the AMR, and these gray circular arcs are the ground LiDAR beams, which hit the ramp. And each of these points, we are seeing the X and Y of these points, but they also come with a Z value, which indicates the height. And given the height of all of these points, we should be easily able to perceive that there's a ramp, and where the ramp begins and ends, and where it is flat, right? So this is an example of another kind of object that a 2D LiDAR will not be able to perceive, but a 3D LiDAR easily is able to detect. And once you detect a ramp, the AMR can take appropriate action, for example, by changing whatever parameters may need to be changed for safe operation on an up ramp or a down ramp. Now we'll come to the blind spot. We have talked about how if you place a LiDAR, 3D LiDAR on top of an AMR, it produces 360-degree visibility, but it also creates blind spots near the body. So let's take this example here. So we have a tugger here, and the LiDAR is placed right on top of it, which generates this blind spot. So you can think of it as a cone. So from the height of the robot down to the ground, if you think of a cone here all around, so the LiDAR is not able to perceive any objects within that. Now, obviously, if there's a person standing in this area, you will definitely see that person in the LiDAR data. But if there is a small object, like for example, this particular object, if it's a very small thing, then it may not be able to see that. Now, how do we solve that problem? So obvious the thing would be to have a camera. We have an RGBD camera here, which is used to detect very small objects in this area. So now this particular triangular area is taken care of by the RGBD camera. But that still leaves this on the side. Now, actually, the robot itself may not hit this object, but it is pulling a white trolley, in which case it really needs to be able to detect this and not move in such a case. So here we are showing some ultrasonic sensors which can be used to detect it. So we have 6 ultrasonic sensors here, and this one detects it and then would stop the robot from moving so that the trolley does not hit this object. So we could use any such proximity sensors such as ultrasonic sensors. We could also use a short range 2D LiDAR, which does the same job of finding objects which are close to the detecting objects which are close to the robot. Okay. So any questions, Guru?
There are a couple of questions. I will go through them. Give me a minute. So first question is solid state LiDAR any better than the spinning counterpart in terms of performance and perception from a safety point of view?
Um, I mean, again, I don't have a lot of experience with the solid state LiDARs, but I understand that they are much more robust because they don't have spinning parts.
Absolutely, yeah.
But typically, since we are in the business of autonomous mobile robots, we haven't done much with solid state LiDARs. And most of them are for automotive use where you're mostly looking straight and they have a very narrow vertical field of view and horizontal field of view. So yeah, I don't really know too much about it except what I read.
Thank you. The second question on fusion, and so you did mention that you could combine data from multiple sensors, fuse it, and get a better understanding of what is around the MR. Now, is there any impact on different frame rates? Now, for example, you did mention LiDARs typically do 10 FPS, but if you have other sensors which have different frames per second, frame rate is different. Are there any challenges that we should consider when we start to merge the data from these two?
Yes, so when you have, I mean, usually you will have sensors, each sensor may have its own frame rate, which means that you'll have to manage which data you take from which sensor, and some amount of some latency may get, built into this, because if you get camera data at 10 FPS, but you're getting LiDAR data at 5 FPS, then you may it depends on when you process it, and there may be some latency. So it's important that all the data is time-stamped and you are aware of the latency in all the data that you're processing, and may you have strict control over the latency of the data that you are looking at and processing. So it's important that you ignore or throw away the any data that is beyond some latency limit threshold, and try to get the latest data and process that, because you do want to take action based on that, something as close to the current time as possible. Yeah. So the solution to the different time frame rates is to timestamp data from every sensor and take appropriate action. For example, if the data is older, one thing is to make sure that we don't process very old data, and the other thing is that if we need any correction, etc., for to apply because of the time difference, then we do that. Yeah, but the main thing is, yeah, we handle it by time stamping the data from every sensor.
Are there any surfaces on which the performance of the LiDAR is compromised? And there is a small reference to glass as being one such candidate. Have you seen any examples where the performance of the LiDAR is not as expected on
right, because because the LiDAR is based on laser beams. Typically, they do not you don't get could return data from glass. So the laser beam mostly would go through the glass. So you don't really see glass in a
Hmm.
LiDAR scan. It's quite similar in many of the sensors. This problem will be there. So some LiDARs do provide an optional second return. That is, if you look at the specification, they would say how many returns. That means when you send out emit a laser beam, what you are receiving is something reflected by some surface, right? So now there are different surfaces. Like for example, you may get one return from the glass, which may be very have low intensity, and then you may get a stronger return from, say, a wall or some object inside a room, right? So some lidars give only one value, which is the strongest, or some lidars allow a setting where you can get multiple returns, and you will have to process them. So that is the way to handle.
Hmm.
But his other options would be to maybe cover, or we could handle it in other ways, which is to say mark certain areas as a no-go and so on. So just
Hmm.
yeah, things like that we can do in the map, but it's
Yeah.
more
It's more about map annotation that you
yeah,
would be wary of certain areas like this.
yeah.
That's all the question in this section. I think we should move on.
Yeah, let's move on. So let's talk about navigation. So navigation is the process of moving the AMR reliably from, say, point A to point B within the customer's facility. Right here, we usually use the words like map and pose and so on. So we'll talk about that. Okay. So localization is the first step in navigation, and it is the process of identifying where the robot is, which is what we call the robot's pose within a map. Now let's define what these two terms mean. The pose is the position and the orientation of the robot. Now, since mostly we are talking of robots which are moving around on the ground, you could have a pose consisting of X and Y, position in X and Y axis, and then the theta, which is the orientation of the robot. You could also have Z if you're, since we did talk of ramps, etc. Now, what is a map? A map is an occupancy grid. Here you see a small snippet of a map. It is very somewhat similar to, say, a floor plan, but it could have a lot more things than a floor plan, which is, so it's an occupancy grid which captures the features of the customer's facility, right? There are different, I mean, there are many localization algorithms. Here we are talking of one thing, which is scan match. Here we often build a map of the customer facility at the beginning. When we survey the facility, we can build the map, which itself is built from such LiDAR scans like this. And then at runtime, what we do is we do LiDAR scan matching to localize the LiDAR within this map. So we have this map, and now within this, we want to say this is the path that the LiDAR normally takes to go from one station to the other. And we would like to know where it is along that. So that process is called scan matching to localize within this map. So let's see how that works. So let's assume that we know the current pose, which is X, Y, and theta. Now, from that frame to the next frame, what we need to do is to identify how much the vehicle the AMR has moved. That is, we would like to know the dx, dy, and d theta between these two frames. And once we know that, we can update the pose, and we now have the current pose, and then we'll continue again. We'll go on with the same loop again. Right? Now, how does this work? So what we do is you can see in how the scan map works. This is the LiDAR scan, and you can see the robot itself. And this is the 3D LiDAR scan, and this is what it is seeing. And what we are doing is we are trying to position it in the at the location where based on the current pose. So this is XY theta. So we know it's approximately here in this region, and we try to orient the robot in this location such that we get a good match of the LiDAR data and the map. So all the red points here. So this is the map, and this is the map with the superimposed with the LiDAR scan, and the red dots show the all the things that match. So this is showing a pretty good match of the LiDAR scan with the map, so that we have got now good localization. Now, so from this we derive the dx, dy, d theta, and hence we update the localization, or we update the pose. So this is how the localization works. So now let's move on. So how do 3D lidars work? So first thing is, as you saw, the lidar sees all these features. Like for example, you can see some window kind of objects here, and a variety of rich information around of the surroundings, and it enables it to do a good match. Now, apart from that, what you see is again these features like these windows, or if you see this particular scan, I have selected some point to show the its x, y, and z values. So you can see that it's about 7-8 meters away, and it is able to see these AC ducts probably at a height of almost 4 meters. So now, why is it important? Right? If it's a 2D LiDAR, it's sensing data in a single plane, and which is near the ground. So if you have a very cluttered environment, then the 2D LiDAR scan would look very noisy and may not be very useful for localization. And another problem is that in places like warehouses, which have very identical looking shelves and stacks, even a human would be lost of sometimes not knowing exactly where he is. So the same kind of thing may happen with an AMR. Now, but when you have a 3D LiDAR, which can see features which are well above the ground, and as we saw here, it can see things as high as say 4 or 5 meters, and there's some rich detail, on the roof, etc. So it can definitely help in localization. So that is an idea of where 3D lidars can perceive rich information in the surroundings, and that helps with the robust localization. Okay, so that's about localization. So any questions on that, Guru?
Yeah, there is one question. It's actually quite an interesting question. So the point that questioner is saying is, if there is data available from other sources, not ego sensors, meaning these sensors are not necessarily on the AMR, but perhaps the plant floor is instrumented with cameras elsewhere, not on the AMR. Would it be possible to take advantage of such sensors in either navigation or safety or localization?
Right. So there are, as I said, there are various ways to localize. There are some class of MRs and AGVs which use external cues like QR codes and other markers, as they're called, to know where they are. It's also possible to have, let's say, a camera which is an infrastructure camera, as you may say, which is fixed on the let's say on the roof of a factory or on a wall, which tells you where you are. Right? All those are possible, but I mean, our goal, our motto has been to not require any changes to the infrastructure. And if you can imagine that now the customer has to maintain that, and then we have to figure out how to convey that information from that camera, and that camera has to be powered and so on. So we are
Also, time syncing that data would be,
yeah.
quite a challenge.
Yeah, we do have, I mean, use cases for having an external camera, for example, at intersections where we have other AGVs running, which you cannot communicate with. So you, in a sense, have to have some kind of spy camera, which tells you that there is no AGV coming, so that you are safe to cross the intersection. So in such cases, yes, it's possible, but I don't think it's a great idea for localization.
Okay. But the point you made, the example that you gave to detect if the intersection is free, perhaps the instrumenting that intersection with the camera makes most sense.
Right. Yeah.
That was all the question in this section.
Okay.
Yeah,
We
I
just
think
have
maybe I can.
one slide. There's just the summary at the end. So as we have seen in the previous slides, The 3D LiDARs provide the AMR with rich information about the environment. And also along with depth cameras, the 3D LiDAR detects a variety of objects. We have seen examples of barriers and ramps, etc., which result in a very safe operation of the AMR. And also 3D LiDARs capture many more features in the environment, leading to more robust localization. And when you combine all of this, the result is that AMRs from Ati Motors have completed more than 500,000 kilometers of collision-free operations, which I hope will convince you that 3D sensors are the way to go.
Absolutely.
Yeah, so that's the end. If you have any other questions?
So I'm checking the chat sessions to see if there are any questions. Actually, no. So yes, thank you, Krishna, for a very informative session. It appears that the key takeaway is that if you're going to build an AMR now, you're better advised to start building them with 3D sensors on board. Hope all of you panelists, all of you members on the webinar found this useful. Thanks for joining and have a good day.
Thank you.